How Does Soap Work by Connor Randall. First, I need to explain the problem of why cleaning is hard. Water is a polar molecule, meaning it has partial positive and partial negative charges. Oils, on the other hand, are nonpolar, meaning they do not have any charge differences in their structure. As we know, polar and nonpolar substances do not mix well. This is why oil floats on water, and many microbes stick to those oils on our skin, so water alone cannot remove them effectively. Now, what does a soap molecule look like? Soap molecules are amphiphilic, meaning they have two different sides, each having different chemical properties. One end is hydrophilic, which means it is attracted to water because it is polar. The other end is hydrophobic, which means it avoids water and is attracted to oils because it is nonpolar. This dual structure allows soap to interact with both water and oil at the same time, which explains how soap makes it easier to clean. Soap is a surfactant. Surfactants reduce surface tension, and surface tension happens because water molecules strongly attract to each other through hydrogen bonding. When soap lowers this surface tension, water can spread out more easily across your hand, and then this increased spreading improves contact between water and the oily substances on your skin. So, what actually happens when soap is added to a mixture of oil and water? The molecules move to the boundary between these two substances, and the hydrophobic tails will insert into the oil, while the hydrophilic tails will stay in the water. This weakens the separation between the water and the oil, so the oil starts breaking into smaller droplets. Soap only begins to form structures once it reaches a certain concentration in water. This minimum concentration point is called the critical micelle concentration, or CMC. Anywhere below this level means that soap molecules mostly float separately. However, anywhere above this level means that the soap molecules arrange into spherical structures called micelles. And this is why using enough soap is important to get proper cleaning. But what is a micelle? In a micelle, the hydrophobic tails point inward towards the oil, and the hydrophilic tails will point outward towards the surrounding water. Oil droplets and greasy substances become trapped inside the center of the micelle. Because the outside of the micelles interact with water, the entire structure can stay suspended in solution instead of sticking back to the surface. So that is how oils are removed. But what about dirt? Dirt and microbes often attach to oils on the skin, and when the soap forms micelles around the oils, the contaminants become enclosed inside along with the oils. These micelles remain suspended in the water, as explained on the last slide. And when you rinse your hands, these micelles carrying the trapped dirt and the microbes are washed away physically along with the oils. Hand washing with soap can also affect certain viruses. Many viruses have an outer lipid membrane made up of fatty molecules. The hydrophobic tails of soap molecules can insert into that lipid membrane and break it apart. When the membrane breaks apart, the virus will lose all of its structure and it will become inactive, essentially breaking apart the virus and curing the disease. Without soap, water alone cannot dissolve nonpolar oils. Without amphiphilic molecules, micelles cannot form. Since microbes and dirts cling to oily substances, rinsing with only water leaves much of the contamination behind. So, soap is necessary to even this polarity difference and remove the substances along with the contamination when you rinse it out. This is my demonstration. So, as I explained on the previous slide, water cannot work on its own. That first picture on this slide was at the start of my demonstration, and that was just with water in there. And then oil and dirt was on top of that water because it would not mix. Water could not get rid of that of those contaminants. However, once I added soap to the mixture, soap's amphiphilic structure can bridge the polarity difference between oil and water, and so it holds the oil and the dirt inside of the micelles. Rather than sticking to the surface, those micelles are now floating around in the water, which explains why the second image there is cloudy. However, soap can only work when it is used correctly. There must be enough soap to exceed the critical micelle concentration, or the CMC. Scrubbing also provides a friction that will detach contaminants from the surface of your skin. Finally, rinsing removes the suspended micelles from the skin after they have been scrubbed. Now, as a final summary, soap works because of its amphiphilic molecular structure with a hydrophobic tail and a hydrophilic head. It reduces surface tension, settles at the boundaries between oil and water, and it forms micelles that trap oils and microbes as well as dirt. These micelles allow contamination to be rinsed away, and in some viruses, soap can also disrupt lipid membranes, effectively providing health.